10,000 watts of solar power. That is enough to run a full-size American household completely off-grid, including your refrigerator, your washing machine, your chest freezer, your lights, your water pump, your entertainment system, your laptop, your phone charging, your power tools in the workshop, and depending on your location and your insulation, even a small heat pump. And in 2026, the equipment to build a 10,000-watt off-grid solar system costs less than at any previous point in the history of photovoltaic technology. We are talking about a complete system: panels, batteries, inverter, charge controller, wiring, mounting, and all the hardware that a motivated beginner can design, purchase, and install for between $12,000 and $22,000, depending on battery chemistry, equipment brands, and whether you hire a licensed electrician for the final connections or do everything within your own legal scope of work. That price range would have bought you less than 3,000 watts of equivalent performance 5 years ago. The technology has crossed a threshold in 2026 where off-grid solar is not just for enthusiasts with large budgets and professional installation teams. It is genuinely accessible to anyone willing to learn the fundamentals, do the math correctly, and execute the installation safely. This crash course is going to teach you those fundamentals from the very first principle of how a photovoltaic cell converts light to electricity, all the way through to the complete design of a 10,000-watt system, the wiring schematic, the component selection, the battery bank configuration, and the commissioning process. I am going to give you everything you need to understand what you are building, why every component exists, and how to put it together correctly. If you have never touched a solar component in your life, this video is your starting point. And if you already know the basics, the second half of this video goes deeper into 10,000-watt system design than most courses twice the length of this one. Stay with me until the very end, because the final section covers the single most common installation mistake in large off-grid systems, and it is a mistake that costs builders thousands of dollars and years of frustration to fix after the fact. If this channel is new to you, I put out honest, technically detailed, genuinely useful content on off-grid solar, alternative building, and sustainable living every single week. Subscribe right now and hit the notification bell, because this is the channel where serious builders come to learn the real engineering behind off-grid systems, rather than the simplified version that gets you excited but leaves you unprepared. Now, let us build your solar education from the ground up. How solar panels actually work. Before you spend a single dollar on equipment, you need to understand what a solar panel actually is and what it actually does, because the mental model you carry into the design process determines whether your decisions make sense or whether you are guessing. A solar panel is made of photovoltaic cells, typically silicon-based semiconductor devices that convert photons of light directly into electrical current through what is called the photovoltaic effect. When photons from sunlight strike the silicon material, they knock electrons loose from their atoms, and when those electrons are captured and directed through a circuit, they produce direct current electricity. A single photovoltaic cell produces a very small voltage, approximately half a volt, and a relatively small current. To produce useful power levels, manufacturers connect many cells in series and in parallel within a single panel, boosting the voltage and current to values that are practical for real-world use. In 2026, the dominant panel technology for residential and off-grid applications is monocrystalline silicon, which achieves efficiency ratings between 19 and 23%. This means that 19 to 23% of the solar energy striking the panel surface is converted to electricity. The rest is lost as heat or reflected. Higher efficiency panels produce more power per square foot of panel surface, which matters when roof space or ground area is limited. For a 10,000-watt ground-mounted system, where space is not a significant constraint, slightly lower efficiency panels at lower cost often produce a better economic outcome than premium high-efficiency panels. A standard residential solar panel in 2026 is rated at between 300 and 450 watts. Most builders designing large off-grid systems use 400-watt panels as a convenient and widely available standard. To build a 10,000-watt array from 400-watt panels, you need 25 panels. that is your starting number, and everything else in the design flows from it. Panel ratings are given under standard test conditions, which use a specific light intensity of 1,000 watts per square meter, a panel temperature of 25 degrees Celsius, and an air mass coefficient of 1.5. Real-world conditions rarely match STC exactly. Hot panels produce less power than cold panels, which is why desert installations sometimes underperform their STC ratings during peak summer heat despite having abundant sunlight. Cold, clear, winter days in high-altitude locations often produce conditions close to or even exceeding STC, and panels in these conditions may briefly produce output near or at their rated wattage. What peak sun hours means and why it is the most important number in your design. You will hear the term peak sun hours constantly in solar design, and it is critical to understand what it means precisely because most beginners misunderstand it, and this misunderstanding leads to undersized systems. A peak sun hour is not a clock hour. It is a unit of solar energy equivalent to 1 hour of sunlight at an intensity of 1,000 watts per square meter, which is the intensity used in standard test conditions. Because actual sunlight intensity varies throughout the day, starting low in the morning, rising to a peak around solar noon, and declining through the afternoon, the concept of peak sun hours converts all of that variable energy into an equivalent number of full intensity hours. If your location receives 5 peak sun hours per day, it means that the total solar energy reaching your panels in a full day is equivalent to 5 hours of direct overhead sunlight at maximum intensity. A 10,000-watt array receiving 5 peak sun hours per day generates 50 kilowatt-hours of direct current energy per day before accounting for system losses. The peak sun hours figure varies enormously by location and season. In the American Southwest, specifically New Mexico, Arizona, southern Colorado, and West Texas, annual average peak sun hours run 5 to 7 per day, with winter months dropping to 4 to 5 and summer months reaching 7 to 8. In the Pacific Northwest, annual average peak sun hours run 3 to 4 per day, with winter months dropping to 1.5 to 2 and summer months reaching 5 to 6. In Northern Europe, the range is even wider, with German locations averaging around 2 peak sun hours in December and rising to 5 in June. For system design purposes, you use your worst-case month, typically December or January, to determine whether your system can meet your household's needs year-round. If your system produces enough power in December to run your house, it produces more than enough in every other month, and the surplus goes into the battery bank or is managed through load shifting. The National Renewable Energy Laboratory's PV Watts tool provides free peak sun hours data for any location in the United States and many international locations. Before you finalize your panel count for any real project, verify your specific location's data rather than using a regional average. Understanding DC versus AC in your system. An off-grid solar system manages 2 types of electrical current, and understanding the boundary between them is essential for understanding how the system components connect and interact. Solar panels produce direct current, which is electricity that flows in one direction only from the negative terminal to the positive terminal continuously. Batteries also store and release direct current. The charge controller, which manages the power flow from panels to batteries, operates entirely in direct current. This DC portion of the system operates at voltages that depend on the system architecture, typically 48 volts for larger residential off-grid systems. Most household appliances are designed to operate on alternating current, which is the power that comes from the utility grid. In North America, the standard is 120 volts AC at 60 Hz for standard outlets and 240 volts AC at 60 Hz for large appliances like electric ranges, dryers, and air conditioning compressors. The inverter is the component that converts the direct current from the battery bank into alternating current at the voltage and frequency your appliances expect. Some loads in an off-grid system can be operated directly on DC without going through the inverter, which is more efficient because you avoid the inverter's conversion losses. A 12-volt or 24-volt DC refrigerator or freezer operated directly from the battery bank through a DC to DC converter is more efficient than running a standard AC refrigerator through the inverter. LED lighting can be operated on DC with appropriate fixtures. Water pumps designed for DC operation are available. In a 10,000-watt off-grid system, where efficiency matters across a full year of operation, identifying which loads can be served directly on DC and which require AC conversion is worth the analysis. The charge controller, the brain of your solar system. The charge controller is the component that sits between your solar panels and your battery bank, and its job is to manage the flow of electricity from the panels to the batteries in a way that charges the batteries efficiently without damaging them through overcharging. In 2026, the dominant charge controller technology for large off-grid systems is the MPPT controller, which stands for Maximum Power Point Tracking. An MPPT controller performs a continuous electronic calculation to determine the operating point on the panel's current voltage curve that produces maximum power output, adjusting its operation to track that point as conditions change throughout the day. This is different from older PWM controllers, which simply connected the panels directly to the batteries and regulated charge by varying the connection duty cycle. MPPT controllers extract 15 to 30% more energy from the same panels compared to PWM controllers, which in a 10,000-watt system represents a significant difference in daily energy harvest. For a 10,000-watt solar array charging a 48-volt battery bank, you need charge controller capacity sufficient to handle the produced by the array. At 48 volts, the array produces approximately 208 amperes at peak output under full sun conditions, which requires either a single large charge controller rated for that current or multiple controllers used in parallel. In 2026, quality MPPT charge controllers suitable for large off-grid applications are available for manufacturers, including Victron Energy, Schneider Electric, and Midnight Solar. A Victron Smart Solar MPPT 250-100 controller, which handles up to 100 amperes of charging current at up to 250 volts of panel input voltage, runs approximately $800 to $1,000 in 2026. Multiple controllers may be required or preferred for redundancy in a 10,000-watt system. Configuring your panel array for MPPT input means understanding series and parallel connections. Panels wired in series have their voltages added together while current stays constant. Panels wired in parallel have their currents added together while voltage stays constant. A typical approach for a 10,000-watt system with 400-watt panels at 20-volt open circuit voltage is to wire panels in series strings of 8 to 10 panels each, producing series string voltages of 160 to 200 volts, and then wire multiple strings in parallel to reach the total desired wattage. The specific configuration depends on the charge controller's input voltage and current specifications. The battery bank is where your solar energy is stored for use when the panels are not producing during nighttime hours, cloudy days, and periods of high demand. The battery bank is almost always the most expensive component of a large off-grid system and the component with the most significant implications for long-term system performance and cost. In 2026, the dominant battery chemistry for serious off-grid applications is lithium iron phosphate, abbreviated LiFePO4. Lithium iron phosphate batteries have displaced lead-acid batteries as the preferred choice for most off-grid applications because they offer dramatically higher cycle life, better usable capacity, stable chemistry with excellent thermal safety, and decreasing cost. A quality lithium iron phosphate battery in 2026 is rated for 3,000 to 6,000 charge-discharge cycles at 80% depth of discharge before capacity degrades to 80% of original at 1 cycle per day, that is 8 to 16 years of operational life, significantly longer than the 500 to 1,000 cycles typical of flooded lead-acid batteries. Lithium iron phosphate batteries in 2026 cost approximately $150 to $250 per kilowatt-hour of usable capacity when purchased as individual cells from reputable suppliers, or $250 to $400 per kilowatt-hour in packaged battery modules with integrated battery management systems from established manufacturers. For a 10,000-watt solar system designed for a typical off-grid household, the battery bank sizing depends on your daily consumption and the number of days of autonomy you want to maintain without solar input. A household consuming 25 to 40 kilowatt hours per day that wants 3 days of autonomy needs 75 to 120 kilowatt hours of usable battery storage. At $200 per kilowatt hour for lithium iron phosphate cells, that is $15,000 to $24,000 in battery cells alone, which is typically the largest single-line item in a large off-grid solar system budget. Lithium iron phosphate batteries require a battery management system commonly called a BMS, which monitors individual cell voltages, manages balancing between cells, and protects the battery from overcharge, overdischarge, and thermal events. Packaged lithium iron phosphate battery modules for manufacturers like Victron Energy, EG4, and Pylontech include integrated BMS units. DIY cell-level battery builds require a separate BMS sized for the battery configuration, which is an additional complexity and cost. At 48 volts, which is the standard system voltage for most large residential off-grid systems, configuring lithium iron phosphate cells requires connecting cells in series to reach the nominal battery voltage. Lithium iron phosphate cells have a nominal voltage of approximately 3.2 volts per cell. A 48-volt battery bank requires 16 cells in series to reach the nominal system voltage of 51.2 volts. Multiple 16-cell strings can be wired in parallel to increase the total capacity of the battery bank. The inverter converts the direct current from your battery bank into the alternating current that your household appliances require. For a 10,000-watt off-grid system, the inverter must be capable of handling the peak power demands of your household's AC loads simultaneously. Off-grid inverters are rated in watts for their continuous output power and in watts for their surge capacity, which is the short-duration high-power output. They can sustain for the few seconds required to start motor loads like refrigerator compressors, well pumps, and power tools. A well pump starting up can draw 3 to 5 times its running wattage for the first second of operation. An inverter that cannot handle this surge will fault and shut down, which is a common frustration in undersized off-grid installations. For a 10,000-watt solar system serving a full household, an inverter rated for 8,000 to 12,000 watts continuous output with corresponding surge capacity is appropriate. Pure sine wave inverters produce the same waveform quality as utility grid power and are compatible with all AC appliances, including sensitive electronics and motor loads. Modified sine wave inverters are cheaper but incompatible with some appliances and can cause efficiency losses and premature failure in motors and transformers. For any system serving a full household, pure sine wave inverter output is non-negotiable. In 2026 quality, pure sine wave off-grid inverters in the 8 to 12 kilowatt range are available from Victron Energy, SMA, Schneider Electric, and several other manufacturers. Victron Multi-Plus or Quattro series inverter chargers, which combine inverter and battery charger functions in a single unit and allow for AC grid or generator pass-through, are among the most commonly specified units in serious off-grid installations in 2026. A Victron Quattro 10000 VA unit costs approximately $2,500 to $3,500 in 2026, depending on supplier. Some builders choose to use multiple smaller inverters in parallel rather than a single large inverter. Victron's three-phase parallel configuration allows multiple multi-plus units to be configured as a single larger inverter system, which provides redundancy in that the system continues to operate at reduced capacity if one unit fails, rather than failing completely when a single large inverter fails. For a critical full household system, redundancy in the inverter stage is worth considering. System wiring. Sizing your conductors correctly. Wiring is not the glamorous part of solar system design, but it is where most system problems originate in both performance and safety. Incorrectly sized wiring causes resistive losses that reduce system efficiency, voltage drops that cause equipment to behave erratically, and in severe cases can cause overheating that presents a fire risk. The fundamental principle of wire sizing is that wire must be sized to carry the maximum expected current without excessive voltage drop or overheating. The National Electrical Code provides guidance on wire ampacity by gauge and installation method, and local jurisdictions in most American states require NEC compliance for permitted electrical installations. For unpermitted rural installations, the NEC still represents the correct safety standard even where it is not legally mandated. In a 48-volt DC solar system, the currents are relatively high compared to equivalent power at higher voltages, which makes conductor sizing especially important. A 10,000-watt array at 48 volts produces approximately 208 amperes at peak output. 420 American wire gauge copper conductor is rated for 230 amperes in typical installation conditions. For runs longer than a few feet, the voltage drop calculation at this current level may require even larger conductors or the use of multiple parallel conductors to keep voltage drop within the 2% maximum that is considered good practice for DC power circuits. Overcurrent protection in the form of fuses or circuit breakers must be installed at every point in the system where a short circuit could cause a conductor to carry more current than it is rated for. In a large off-grid system, this means fusing at the panels at the charge controller inputs and outputs between the battery bank and the inverter and at every branch circuit of the AC distribution system. The battery to inverter connection in a large system carries the highest currents in the entire installation and must be protected with an appropriately rated fuse or breaker within 18 inches of the battery terminals. Grounding your system correctly. Grounding is the aspect of solar system installation that beginners most commonly underestimate and that creates the most serious safety risks when done incorrectly. A properly grounded off-grid solar system protects personnel from electric shock in fault conditions, protects equipment from lightning-induced surges, and is required by the National Electrical Code for permitted installations. In a photovoltaic system, equipment grounding connects all metal enclosures, conduit, mounting structures, and equipment frames to a common grounding electrode system that is connected to the earth. This means that if a hot conductor contacts any metal surface in the system through a fault or accident, the current flows to ground rather than through the body of a person who might contact that surface. The system grounding electrode typically consists of one or more ground rods driven 8 feet into the earth near the electrical service entrance of the system, connected to the main grounding point with 6-gauge or larger copper conductor. For a large off-grid system in an area with poor soil conductivity, multiple ground rods may be required to achieve an acceptable grounding resistance. Lightning protection for a solar array involves surge protection devices installed at the array combiner box at the charge controller inputs and at the inverter AC output, which clamp voltage spikes from nearby lightning strikes before they reach sensitive components. Direct lightning strikes to solar arrays can overwhelm even the best surge protection, but good surge protection devices prevent the far more common damage from induced voltage spikes in nearby strikes. Commissioning your system safely. Commissioning is the process of starting up and verifying the operation of a newly installed system before you depend on it for your household's power supply. Rushing the commissioning process or skipping verification steps is the source of many of the most expensive and frustrating problems in off-grid solar installations. The correct commissioning sequence for a large off-grid system begins with the battery bank disconnected and isolated. Verify all wiring connections are secure and correctly terminated. Verify all fuse and breaker ratings match the design specifications. Verify all equipment is mounted securely and all conduit and wiring is routed and secured correctly. Verify that grounding connections are complete throughout the system. With the battery bank still isolated, connect the solar array to the charge controller and verify that the charge controller powers on correctly and shows the expected array voltage. Any unexpected behavior at this stage should be investigated before proceeding. Connect the battery bank to the charge controller and verify that the charge controller begins the charging process, correctly showing the expected battery voltage and beginning to deliver charging current. Monitor the charge controller's display or remote monitoring interface to verify that charging parameters match the battery manufacturer's specifications for your specific battery chemistry. After verifying charge controller operation, connect the inverter and verify that it powers on correctly and produces AC output at the expected voltage and frequency. Test AC loads progressively, starting with small resistive loads and progressing to motor loads, verifying that the inverter handles each load correctly. The most common installation mistake in large off-grid systems. Here is the mistake I promised at the beginning of this video, and it is responsible for more failed off-grid solar installations in 2026 than any other single error. It is not a wiring mistake. It is not a grounding mistake. It is a sizing mistake, and specifically, it is the mistake of sizing the solar array for average conditions rather than for worst-case conditions. A 10,000-watt solar array in a location receiving 5 peak sun hours per day on average sounds like plenty of power for a household consuming 30 kilowatt hours per day. 50 kilowatt hours of gross production minus 20% for system losses equals 40 kilowatt hours of delivered energy, which is 33% more than the daily consumption. Sounds like there's margin to spare. But average conditions include both the summer months, when the location receives 7 peak sun hours, and the winter months, when it receives 3 peak sun hours. In December, at 3 peak sun hours, the same 10,000-watt array produces 30 kilowatt hours, gross minus 20% for losses, equaling 24 kilowatt hours delivered. That is 6 kilowatt hours short of the daily requirement. Over a week of December winter conditions, the battery bank runs short of the daily consumption by 42 kilowatt hours, and the system is drawing down the battery bank faster than it is charging it. If the battery bank is sized for only 3 days of autonomy at the designed consumption rate by the 5th day of winter operation at average December solar production, the battery bank is approaching its minimum state of charge and the system goes into low battery shutdown. This is the scenario that causes off-grid households to run their generator for weeks every December and January, which was never part of their plan. The correct approach is to size your solar array and battery bank for your worst month solar resource, not your annual average, and to calculate your daily household consumption honestly using the actual loads that will be in the home rather than an idealized, efficient lifestyle that may not match the reality of your household's actual behavior. Add 20 to 30% contingency to both your panel count and your battery capacity beyond what worst-case calculation requires, and you have a system that performs reliably through every month of the year rather than a system that is technically adequate on average but struggles through every winter. Final thoughts. Building a 10,000-watt off-grid solar system in 2026 is within reach of any motivated beginner who is willing to invest the time to understand the fundamentals. The technology is excellent. The pricing is historically favorable. The online resources for learning installation technique, including detailed manuals from every major equipment manufacturer, are freely available. The federal tax credit of 30% reduces the net cost significantly for qualifying installations. What separates successful off-grid solar installations from failed ones is not budget, and it is not technical complexity. It is the quality of the design decisions made before the first component is purchased. Size for worst-case conditions. Use worst-month solar resource data from a reliable source. Measure your actual household loads rather than estimating them. Choose battery chemistry and capacity that provides adequate autonomy for your climate and your lifestyle. Wire every circuit to the appropriate standard. Ground the system correctly. Commission it methodically. Do those things and you have an off-grid solar system that does exactly what you built it to do for 20 to 30 years, producing free electricity from sunlight and giving you the energy independence that a grid-tied household can never fully achieve. If this crash course gave you the foundation you came here looking for, please hit the like button because it helps this content reach more people who are building their off-grid education right now. Subscribe for more honest and technically detailed content on off-grid solar, alternative building, and sustainable living. Drop a comment below telling me your location and your estimated daily consumption because I respond to every comment personally and I can give you a rough system sizing recommendation for your specific situation. See you in the next one.